Good day, students. Today we shall discuss about Fermat's principle in light. Fermat's principle can be used to explain the rectilinear propagation of light through a medium. That is why light propagates along a straight line in a medium. It can also be used to explain the laws of reflection and also the laws of refraction. The Greek philosopher Hero of Alexandria first postulated the principle of shortest path. According to this principle, when light travels from one point to another through a set of media, there may be different media, light will choose that path for which the path length is minimum. But this principle could not simultaneously explain reflection and refraction of light. Well, according to the statement here, reflected light travels from one point to another along the shortest path. The figure explains this. Light from A falls upon the surface M dash and gets reflected to a point C. It can be reflected upon different points. It can be reflected upon E, it can be reflected upon D, or it can be reflected upon B. So light can take the path AEC or ADC or ABC. In order to find the path of shortest length, we take the mirror image of C upon C1. When we draw a straight line from A to C1, it passes through B. If we try to draw a line from A to C1 through D, it needs to be broken into two lines, right? Similarly, if A needs to pass through E, it should be again broken into two lines. So of the paths ABC1, ADC1 or AEC1, the path of shortest distance is ABC1. Just for mathematical reference, we are creating the point C1. So from this we infer that light will take the path ABC upon reflection. Okay. But in the case of refraction, here refracted light travels from one point to another along the path for which time taken is minimum. Here we have to take that into consideration because light travels from one media to another media. So when light from point A refracts through this glass surface and moves to the point C, it will undergo bending. It will not follow a straight line path. So naturally we can assume that it will not be through the path A, D, C. Okay, fine. And then depending upon the refractive index of the entering medium, light will bend. And light will choose that path in the second medium for which time taken is minimum. We shall derive it in the following classes. Okay. So in order to give a better explanation, it was Pierre de Fermat in 1650 who suggested the principle of least time. According to him, he stated that when light travels from one point to another through a set of media, it follows that path for which it requires least time. That is, the path for which the time taken is a minimum. Mathematically, it is represented as dt by ds is equal to 0. So let us assume 2 points P and Q. Light can travel from P to Q in this manner, or it can choose the path like this, or it can choose a path like this. It has different possibilities. Let me assume a small infinitesimal time interval dt, for which it travels a distance dl. Hence, I can write the infinitesimal time taken to travel dl distance as dt is equal to dl divided by v, which is the velocity of light in that medium. Okay. Now, to find the total time taken to travel from point P to Q, I just need to integrate t. Hence, total time t is given by integral P to Q dt. That is integral P to Q dl divided by v. Here, v can be substituted for c divided by mu, where c is the velocity of light in vacuum and mu is the refractive index of the medium. This implies t is equal to integral P to Q mu divided by c dl. We know that c is a constant, hence taking it outside I can write 1 by c integral P to Q mu dl. The term integral P to Q mu dl is called the optical path length in a medium. Okay, fine. Hence, optical path length can be written as optical path length delta is equal to integral P to Q mu dl. Hence, the total time can be represented as delta divided by c. Now we've come across a new term. What is optical path length? It just defines the path traveled by light through a medium. It can be different in different media. Okay. Mathematically, it is written as the product of refractive index mu of the medium and the geometrical path length L. Thus, delta is equal to mu into L. For the same time t given, if light travels L1 distance in a medium of refractive index mu1, and in that same time interval, again light travels L2 distance in another medium of refractive index mu2, the product will remain conserved. That is, mu1 L1 will be equal to mu2 L2. Now, assume that light travels through a point given here by A to a point B, which has many layers of different refractive indices within it. So what happens is the optical path length in each media will be different. So in order to calculate the total optical path length, we need to sum each values in each layers. That is, in the first layer, if the refractive index is mu1 and the geometrical path length is L1, the optical path length there is mu1 L1 plus. In the second medium, if the refractive index is mu2 and the geometrical path length is L2, you get the next term mu2 L2 plus likewise till the last layer of refractive index mu n and geometrical path length Ln. So the optical path length between A and B points can be written as a series of a sum of products. This can be simplified using summation I from 1 to n mu I Li. Okay. Now this can be written if each layer has distinct boundaries. If these layers don't have boundaries, that is, the variation of refractive indices between A and B is very small, you won't be able to quantify the value for Li. So in that case, we can integrate the path from A to B. You can integrate the path from A to B mu dl. This gives the optical path length from A to B. Now, we know that from total time taken, T is equal to optical path by C. Hence, T is proportional to delta. Thus, Fermat's principle, which was delta T by delta S can equal to 0, can be rewritten as delta D delta by ds is equal to 0. Earlier, we have calculated that T can be written as optical path length by C. Okay, that is, T is proportional to optical path length. Thus, Fermat's principle can be rewritten from what we saw earlier as what we saw earlier as dt by ds is equal to 0. It can be rewritten in the terms of optical path length as here d delta by ds is equal to 0. Okay, so this is the mathematical form of Fermat's principle. But again, we are equating it to 0 to show that the time taken is minimum. The least possible value for minimum is 0. Okay. But what happens is, in different cases, we have seen that this principle is not being followed. For example, let us see this case. Well, the image on the right side is that of an elliptical reflector. Ellipse has a property that light rays emanating from point P1 will always focus upon point P2. The peculiarity is that point P1 and P2 are the focal points of the ellipse, and they are conjugate points, that is, each one are the mirror image of the other. So if we place a source here, light source here, light will be reflected. Light can take any path, and it will take any path, and all the light rays will converge upon point P2. Now here, if we measure the path length in these different lines, all are the same. Path length remains same. Okay. Now in another case, if we use the figure on the left side, we have drawn the elliptical reflector. and upon it I have drawn two other curves. I have drawn a spherical mirror of curvature n, spherical mirror n prime of greater curvature than the ellipsoid. Okay, and another spherical reflector MOM of lesser curvature than the ellipsoid. What happens is in the spherical reflector NON, light takes the path for which time taken is maximum to travel. Light prefers the path for maximum time. But in the spherical reflector MOM, light prefers to take the path of shortest time. So it depends on the curvature of that spherical mirror. The curvature is less than that of an ellipsoid, it will follow the principle of least time. And if the curvature of the spherical reflector is greater than that of the ellipsoid, it will follow the principle of maximum time. So to make a generalization of these cases, Fermat then postulated Fermat's principle of extremum path or Fermat's principle of stationary time. According to this, we can say that when light ray travels from one point to another through a set of medium, it follows that path for which time taken is a minimum, is a maximum, or stationary. Okay. So that is the basic principle that we are going to use. Next, let us discuss the rectilinear propagation of light or straight line propagation of light. So we are consider light traveling in a medium of constant refractive index. So that is defined by a homogeneous medium. There the refractive index mu is a constant. Fermat's principle is given as d delta by ds is equal to 0. That is derivative of integral mu dl divided by ds is equal to 0. Derivative of integral becomes irrelevant, hence I can write mu dl by ds is equal to 0. So a product term should be equal to 0. This here, mu cannot be equal to 0, right? This implies dl by ds must be equal to 0. That is, dl by ds is defined as the variation of the path length between 2 points should be minimum. If we have 2 points A and B, the variation of the path from the point A to B should be minimum, means that this path can only be a straight line. Okay, so hence Fermat's principle explains that if light travels from one point to another in a medium of constant refractive index, it will choose only a straight line path to follow. Okay.